I'm just going to read you the rules and then boom. The first three numbers indicate the number of protons, and the last three indicate the number of neutrons. So, like, inside of a parentheses, that's what it means. Half-lives are measured in seconds with scientific notation. So, for example, a half-life of 4.5 billion years would be 1.41 E17. Negative exponents have a negative sign to the left of the number, obviously. Half-lives are rounded to 3 significant figures. If an isotope does not exist for any measurable amount of time, it is marked as 0. And half-lives between 0.001 and 999,999 seconds are measured without scientific notation because it's actually more efficient to do so. Type of decay is marked with N neutron, P proton, D deuteron, T triton, A alpha, C cluster, S fission, B plus or minus beta, E electron capture, and EB is electron capture and beta plus. That can both happen. And G is gamma. Cluster decay is represented and spontaneous fission are represented as C and S, but the smaller atom that was emitted is placed on the row below, and if it is unstable, it will become part of the decay chain. Energy is represented in MeV using scientific notation and is placed to the right of the decay type with an energy release between 0.001 and 999,999 MeV just being written without scientific notation because it's more efficient. When electron capture and beta decay are both present, the energy release is measured counting electron-positron annihilation. Energy release is always rounded to 3 significant figures. If there are multiple types of decay, both types are listed with the energies to the right and the decimal of decays which are said type to the left. If the decimal is less than 0.001, scientific notation is used. All but the highest decimal is always rounded to 3 significant figures, because if you round them all, then they will either add up to more than 1 or less than 1, and we can't have that. Excited isotopes are indicated as M, 1M, 2M, and 3M, depending on the level of excitation. These symbols are placed on the leftmost part inside of the parentheses. When multiple particles collide, it is written as the particles on the top that are colliding, with one row below C with the amount of energy released by the collision, and then below that the amount of products released by the collision. Endothermic reactions are indicated with a negative sign in front of the energy. Exotic particles are represented using abbreviations, which I will show you the list of exotic particle abbreviations at the bottom. Now you might be confused and think, oh, if there's no spaces between stuff, I might get confused and not know where the information for one isotope ends and the other starts. But if you take into account that all of the information is rounded to 3 significant figures, it should be pretty easy to figure it out. And yes, even if, say, it's like 1,567, it would just be rounded to 1,570 because otherwise it would be indistinguishable from 156 and 7 blah blah blah. So I have condensed the entire uranium-238 decay chain into just 436 characters. Yes, I counted. Well, no, I had a computer count for me, but... And I think this is pretty cool. Now, there are a few shortcomings, but I will make sure to try and resolve them, and if you see any, please tell me. Oh, I did not mean to do that. And here you can see the list of exotic particles. If you, say, want an antiparticle, just instead of placing nothing where the underscore is, place an A lowercase. And complex particles are represented as the particles that compose them inside of parentheses.